Okay, hi everyone. Today we're going to solve another problem, that is LeetCode 100 same tree. It's an easy level problem and it's based on tree, and it has a good like to dislike ratio, although I do not find this problem to be that good, but I'm not judging it. So let's start with this problem. We are given the root of two binary trees. So first of all, what's a binary tree? If a node in a binary tree have at most two children or zero children or even a one children, then it's considered as a binary tree. And we are given two trees. Basically we are given their roots, that is one, and one is given to us. We need to write a function if they are the same or not. Okay, so we need to make a check if these trees are same or not. So two binary trees are considered the same if they are structurally identical and the nodes have the same value. So for example, if we have a tree like this, 1, 2 and 3, then you have this tree, 1, 2 and 3. These trees are not same. Why? Because they are different in their structure. But if you have a tree like this, 1, 2 and 3, and then you have 1, 3 and 2, they have a same structure, but their node values are different, because one left child should be 2 for this tree, but one left child at this tree is going to be 3, so they are also not same, which means that the only same tree that we can have is 1, 2 and 3 if they are genuinely same by structure and by their node value. So this is the question, and we need to return true if they are same, and we need to return false if they are not same. And yes, so just like this case, so one left child is 2, but for this tree, one left child is 1, which is not same. So let's write a function. So what I can, so before jumping on to the code part, let's see how we can solve this. So let's say we have this tree. The first approach that comes to everyone's mind, I think, is going to be recursive approach, and that's very like intuitive, because tree problems are 90% tree problems are based on recursion. So that's why. So we can start recursion, and we can keep this node in concentration and check if they are same or not. Yes, they are same. If they are same, then my recursive function says that if the concentrating nodes are same, then their right child, then their sorry left child and their right child should also be same. And if the right and left trees, basically the sub trees, are same, then it means that this is a same, these are same trees, right? They are same tree. But if there is a problem, then they are not. So let's see for this, let's dry run the approach for this case. So I'm focusing on this node currently, and I will say, okay, these are same. So let's go on further. Then I will go to the left child. Now at left child, their values are different. Because their values are different, which means that these trees are not same. Now let's consider this situation where you have something like this. Now you are focusing on the second child and they are same. Then you will say that, okay, so these are null values. Then you will say that let's focus on the two left child, second left child, the node 2 left child, and that is null. But at this point, this is also same, so you will be like, okay, this is fine, and then you will backtrack, and now you are concentrating on the second node's right child, and at this point you will realize that they are not same. This is null value and this is not a null value, which means that this is false. So by this algorithm you can also check for the structural identity if they are same or not, and you can also check for the node value. So this is the recursive solution. So let's write it. So first thing first, we need to check if the nodes are null. So if q is also null, p is also null, then I will say just return true. But if p is null and the if both of them are not null but one of them is null, which means either p is null or q is null, then I will say return false. Right, this is like this situation where one of the child was, or one of the node was a null value, but the other one was not a null value, so we need to return false for that case. Now if another condition is if p value, because they are not going to be null, so we are not going to have a null access runtime error. If p value is not equal to q value, then I'll be returning false again, because their values should also be checked. And at last I will say that both of the concentrated nodes were equal, were identical. That's good, that's fine. But now make sure that their right subtree and their left subtree, left and right subtree, they are also equal. So for that I will call it recursively. I will say same tree function on p of left, that is the left subtree, and q of left, and is same tree over p of right and q of right. And there has to be an and operation, because if one of these right or left subtree is not giving me the correct value, is not same, then it should return false for the entire question, for the entire problem. Okay, and it is performing good, 0 millisecond. Fine, so this is the recursive approach. Now the recursive approach will have a time complexity of order of n, right? Because these are number of nodes, and space complexity and time complexity will be same. So why space complexity? Because of the recursive call stack that you are using for recursion. So that is somewhere like order of n. That is not order of n, because the space complexity will be something like order of h, that is the height of the tree. But still, for for average case, we say that height of the tree could be equal to the, I mean, in the worst case, height of the tree could be equal to the number of nodes present in it. When you have a tree like this, 1, 2, 3, and so on, then the height of the tree is equal to the number of nodes present in it. So yeah, because of that, most of the solutions or editorials talk about this thing, that it is order of n, space and time complexity, because this is a big operation. Otherwise, on theta operation, this will be h. In average case, this will be h, and on average case of time complexity, this is space, and time complexity is going to be n. These are the time and space complexity for this node. Now if we want to write a iterative code, then we can also do it. So for iterative version, you can use a stack and have some DFS or traversal technique like pre-order, in-order, or post-order. But when it comes to tree traversal and iterative version of it, then the most like intuitive thing is to use a BFS. So I'll be using a BFS, and for BFS we use queue data structure. So tree node star. Now you have a q1, then you have a q2. Q1 is going to have a value of p, sorry, and q2 is going to have a value of q. But before this, we need to make a check. So the checks are, if p is equal to null, the same checks. If p is equal to null and q is equal to null, then return true. But if both of them are not null, one of them is null, if p is null or q is null, in that case return false, and everything else would be taken care by the traversal, that is the BFS. So while q1 dot empty is false and q2 dot empty is false, we are going to extract these nodes. So this is tree node pointer. So first we have current 1, that is going to be equal to q1 dot front. Then we have current 2, that is, sorry, pointer current 2, that is equal to q2 dot front. Then we will pop them out, q1 dot pop and q2 dot pop. Okay, so after this, now we are going to make a check. If current 1 value is not equal to current 2 value, then we are going to return false, that they are not equal. While traversing, we find some values that don't have, we find some nodes that don't have matching values, but they should be having a matching value, so we are returning false for that. Other than that, if they are not, then we will be simply checking their right and left child. So I will say current 1 left child is there, and current 2 left child is also there. If both of them are there, then I will say q1 dot push current 1 of left. Other than that, I will say current 2 of left in q2. Now there's another condition, that is if both of them, so let's say none of So let's say we have current 1 of left is null and current 2 of left is also null. But as we have said that null values are identical and it's fine. But what if current 1 left is null, but current 2 is left is not null? In that case, we need to make a check if current 1 left is null or current 2 left is null. If this is the case, then I'll be returning false. Then I'll be copying the same code up for the right child. And after this traversal, if everything is fine, we are out of the traversal, and then we will return true that we haven't found any node or any structural like disformality in the structure of a tree, and every node is equal to their corresponding node, so it's fine. Return true. Okay, we are failing on this one. Let's see why. So we are outputting false value, but it should not be a false value. Interesting. So these conditions are not tempered for this test case. Then we'll go back to this one. Their values are okay. Yeah, they are not equal. Yeah, it's good, I think. Hmm. Okay, this should be so current 1 of left. If both of them are null, okay. So current 1 of left is there. Current 2 of left is there. So we are pushing it into this queue. That current 1 left is null. Okay, so the basic problem is if current 1 left is null and current 2 left is also null, right? In that case, I'm returning false because current 1 left is null. Okay, so for this problem, I will say something like this. If current 1 left, okay, so if both of them are null, then it should not return false, which is happening in this case, I think. So for this case, I will say if uh, okay, so yeah, I have to debug this, and now I know what is the mistake, and I hope that some of the people who are watching this have also figured it out. What was the mistake? So the mistake is when current 1 is left is null and current 2 left is also null, in this case, this should return true. This is not a false condition when both of the childs are null. But according to my implementation, the code that I have written here, if both of them are null, it will return false, which shouldn't be the case. So we are going to say that if yeah, so if both of them are null, let's say, but one of them has a value by this condition, then it's a problem. And same thing for this one. And if we submit it now, I think it will work. Yes, and let's see what is the time complexity or runtime. Okay, it's also optimized 0 millisecond. Fine. Yes, space wise. Okay, it's a 0. Okay, it's 9 MB and it's my solution is 10 MB. It's not that much of a difference. Mm, yeah. Yeah, so I think it makes sense. Good solution. So for the iterative version as well, the time complexity is order of n because we are traversing on the number of nodes, and the space complexity is going to be the maximum nodes in a certain level. So that could be, L, let's say L. So this is a space complexity, this is a time complexity for iterative version, and this is a space and time complexity for recursive version. So this is a problem. I hope you have learned something from this problem, and thanks for watching. Have a good day.